All right, let's look at a little bit of Snell's law and refraction of light. Just refraction and reflection, both. Okay, so we'll say, starting off, we just have light, a ray of light going in air. Let's say it's magenta light. So if it's let's get specific. Say it's RGB magenta light, so it's really red and blue together makes magenta, right? And so it's going to hit this glass. It's going to be a certain part of it's going to be reflected, and some part of it's going to be refracted, bent. So the reflected part is going to just come back off at the same angle. Same angle with respect to the normal. All right, so we got this perpendicular normal line to the surface of the glass, between glass and air. And the theta incident is equal to theta reflected. Okay? And so that's easy for reflected light. It's always just equal angle to the normal, right? And so that's the reflected part. The refracted part, refracted light means bending of the light, bent light, and so it's what's coming into the glass. And so for that we have Snell's law. Snell. For refracted light, so it says N1 sine theta 1 equals N2 sine theta 2. There's a version with velocity because index of refraction is C over V, and so we can say so N1 is C over V1 and N2 is C over V2, so we can say C over V1 sine theta 1 equals C over V2 sine theta 2, or multiplying through by the V's, you get V2 sine theta 1 equals V1 sine theta 2. So in terms of velocity, we can use this version of the equation, but in terms of index of refraction, we can use this version. Okay. And the definition of index of refraction is just how we get between the two. So we're going to have a refracted light, and actually we're going to say that the index of refraction is different, or it is different, for different wavelengths of light. And so we'll say for red it's 1.49 in this kind of glass, kind of made up, but anyway, and then for violet or blue it's 1.51. All right, I guess we'll say that this is violet, the second ray that I'm drawing on there. Okay, so which one's going to bend more? All right, which one has the higher index of refraction? Right, it's going to slow down more. Right, if we want to solve this for velocity in the medium is C over index of refraction, and so bigger index of refraction means it goes slower, and so it bends more, bends more towards the normal. So, for example, if N1 is air, so N1 is going to be the smaller index of refraction. N2 is going to be either 1.49, 1.51 for different colors, or maybe an average of 1.5. But for N1, theta 1 staying the same, if N2 is bigger, then theta 2 must be smaller, so it must be closer. So violet has its N is bigger, N in glass is bigger, and so N2 sub violet, I guess. So theta 2 for the violet is going to be smaller, or for the blue is going to be smaller. So our theta 2 for violet would be here, whereas theta 2 for red, maybe, I'm just making stuff up here, but you get the idea. Theta 2 for red would be maybe something like that. And so the red is bent a little bit, the violet is bent more. Okay? Reflected, it just bounces back, they bounce back together because they aren't entering into this other material, the glass, that changes the speed of light inside. Okay, so we drew the refracted rays. part B, find the angles. So like we said with Snell's law, we can say n1 sine theta 1 equals n2 sine theta 2, but we'll do red first. And so we want to find theta 2r. Theta 2r, doing a little algebra, divide through by n2 for red, and then take the inverse sine, arc sine, inverse sine of n1 over n2 for red sine theta 1. So inverse sine of n1 was 1 for air. For red we said 1.49 sine theta 1. Theta 1, I should give a number for theta 1. Let's say theta 1 is 40 degrees. So we'll do 40 degrees. So theta 2 for the red is inverse sine of 1 divided by 1.49. Let's put that in parentheses. Times sine of 40. Looks like I did it right. 25.6 degrees. All right, let's try that for the violet light. So again, same. It's all together when we enter. So n1 is air, is 1 is same, and sine theta 1 is the same. But now we've got n2 for violet light or blue light, sine of theta 2 violet. All right, so same math. It says theta 2 violet then is inverse sine of 1 over, now n2 violet is 1.51, and sine of 40 degrees is still the same for theta 1. So for violet, cheat and get that equation back. Divide by 1.51 instead of 1.49. It's the only thing that changed. And so it's not very much different. 25.2 degrees. Okay. So it is a small effect, but it is the effect that makes rainbows, right? It makes prisms. And so we can separate out the other colors. We'll have their indices of refraction in between these two, and so we get the green, and we can get some yellow, so forth. We can get the spectrum of colors separated inside there because each color has its own index of refraction. So each wavelength will have a different index of refraction, just a little bit different, so it pulls it out. And then if we had another edge, another interface here where the glass stopped and went back to air or something, we would have the effect again. Each one was a little different, especially if it was at an angle. If it's a prism kind of thing, we could have this at an angle coming out, and so we could get the effect to multiply a little bit more as we're going out the other side. Okay, but that is, hopefully you can kind of see where we're getting the idea for, or how rainbows are formed. All right. So, find the critical angle for which, let's just go ahead and go with this critical angle just for white light. So let's just go for this one for part C. Let's just use N2 is equal to 1.5 and just kind of look at it for all, or the average light beam or the average light wavelength coming through. Or for all of them kind of together, assuming that the index of refraction isn't very different for all the different colors at this point. So what is a critical angle? Critical angle is the angle that gives total internal reflection. Critical angle gives total internal reflection. And so we're thinking of light that somehow has gotten inside, right? And it's going to bounce off. Some of it's going to bounce off and reflect inside the thing. This is especially useful in fiber optics and so forth, or in diamonds. But so it hits the interface going from some n, we can call it ends of glass, and then ends of air here maybe. And so some of it's going to bend or reflect, and then some of it's going to bend and come back out. And since air has a smaller index of refraction, its theta should be bigger than this theta. Well, these are both the same, but anyway. And so the critical angle is the smallest angle where we can get this refracted ray to go away. All right, so there's some angle, make it pink or something, some angle here where it's gotten bigger, right? Our incident angle has gotten bigger, and this one also will get bigger, and so eventually this one goes to 90 degrees. And so theta critical is when theta refracted, or theta 2, is equal to 90 degrees. And so we do have a formula for this derived on our equation sheet. Let me see where that went. Right here. So theta critical is arc sine n2 over n1. Where did that come from? We have n, let's just go with n glass theta, or sine theta glass. Well, let's just do this for the critical. So theta critical is equal to n air sine of, we want the angle, the critical angle is just when it so this just bends enough so that it stays inside. So you shine it this way and it refracts, but then as you get here, then it's this way, then anywhere past this, it's going to stay inside, right? And so this is going to be 90 degrees. All right, so what is sine of 90 degrees? 1, right? And so we get, and let's divide both sides by ng. So we get sine of theta critical equals na over ng, or we could say n inside over n outside. Oops, I did that wrong. A is outside, outside over n inside. So it's internal reflection, internal to the glass or to the fiber optic cable or to the diamond, what have you, right? And so then this says that theta critical then is inverse sine or arc sine of n outside over n inside. Right, so in this case, theta critical is inverse sine of outside was air, so it's just 1, and inside we said it was the glass was 1.5. So we can get inverse sine of 1 divided by 1.5. 41.8 degrees. Okay, so angle's bigger if it hits, if somehow a light beam gets in and it hits from angles to the normal bigger than 41.8 degrees, then there's going to be no light getting out the other side. It's going to just bounce inside. So it's totally reflected, total internal reflection, totally reflected on the inside. All right, and so this is what makes diamonds sparkle. Diamonds have a pretty high N, index of refraction, like 2.5 or something like that. And so it has an even smaller angle of critical angle. And so lots of light that gets in gets trapped and bounces around and makes the diamond all sparkly and pretty, right? And this is also useful in fiber optics, so that in fiber optics you have a long, narrow fiber, and we want the light to bounce inside there. The flashes of light to bounce inside, not get outside the fiber. And so they make it so that N on the inside, right, we want N on the inside to be much bigger than n on the outside. So the critical angle then is smaller. Yes, so n on the inside large, and so then theta is large. No. N on the inside is large, so then theta is small, because we're dividing by n on the inside. Yes, this is n. And so critical angle is small, and so most of the angles, if we have a small critical angle, most of the angles are over here, so hopefully most of them cause it to reflect and not try to escape. But again, the bigger n on the inside is with respect to n on the outside, the better. Did I do that right? It seems a little backwards. No, it needs to be that way. So, because this ratio can't be the other way. If it was 1.5 over 1, inverse sine is not defined, right? Because sine can't be bigger than 1, so inverse sine can't operate on anything that's bigger than 1. Okay, so that's the critical angle. We already kind of did this, found the two angles for the different colors of light. All right, I guess that I was expecting the first one to find the angles. I was just going to do it for n equal. Well, let's go back to that one, I guess. So for part A, let's just say n1 is 1 for air, and n2 is 1.5 for glass. Then the angle altogether, if we were just assuming there was only one, we would have n1 sine of 40 equals, which is 1 sine 40 equals 1.5 sine of theta 2, which is how most of these problems probably will be, is just one index of refraction for the whole medium. And so theta 2 is sine inverse of 1 over 1.5 sine 40. All right, which is very much like what we just did. Sine inverse of 1 divided by 1.5 times sine of 40. Somewhere in between, right? 25.4 degrees. Okay, so there we have it. Reflected and refracted light, critical angles. This separating of light is called dispersion. The rainbow effect is dispersion.